Hello, I am Kalen Dittrich, and these are my problems for Project Turn-In 2. For problem number 1, you're supposed to consider a chemical reactor that can be modeled as a sphere. For part A, you are to derive the steady-state one-dimensional radial heat conduction equation with heat generation of E. And then for part B, there's no longer energy generation, and you are to describe the equation that relates the temperature profile throughout the reactor. So this is supposed to cover learning elements of deriving and solving the conduction equation and the learning element of conduction heat transfer, as this is a heat conduction problem. Here you can see a simple picture of the sphere. You have a radius change right here of delta R and an inner radius of R. This is for part 1. I begin with just a general energy balance of E in minus E out plus E gen is equal to 0. From here I go about using volume and area equations and relating this to heat transfer and heat flux Q dot S to determine the overall heat conduction equation. Here you see me taking the limit as R approaches 0, and then using Fourier's law and constant thermoconductivity to reach this final equation. And then I also find the boundary conditions based off of A as well, which you have at R is equal to R1, you have heat flux at this boundary, and then at R is equal to R2, you have convection heat transfer. And then for part B, we use these boundary conditions that were stated right here to determine the temperature profile. Again, here's a separate picture for part B. This is where we're now solving the heat conduction equation learning element. And here's the final equation describing the temperature profile of the sphere. Number 2, you are to consider a shed that has an inner concrete wall and an outer sheet metal wall, and you are to determine the rate of heat transfer through the wall. You're told to neglect radiation on the inside, and then you have an emissivity of 0.6 on the outside as there is radiation. You're given a temperature of the outer surface as well, and after determining that heat transfer, you are to check if this is a valid assumption for the outer surface temperature. So this covers the learning outcomes of resistance networks for 1D steady state, as well as radiation and convection heat transfer. In my analysis, I began by drawing this picture. You have the thermal resistance networks below, which we're going to model this system as, and then you have the concrete wall itself, which you're given the area as well. And first I begin by solving for these resistances. The inner resistance is just a convection resistance, and then R1 and 2 are conduction resistances due to the concrete and metal. And then the last thermal contact resistance, R outer, is both convection and radiation. And so to determine this, we need to find a heat transfer coefficient combined, which involves first finding the heat transfer coefficient for radiation as seen here. And then you add that to the convective heat transfer coefficient for the outside that we were given. And that's used to find the R outer resistance. And from here, you go and add these up as they are all in series to find R total. And then we know that for thermal resistance networks, heat transfer is equal to the difference between the infinity temperature on the inside and the infinity temperature on the outside divided by R total. This finds a large amount of heat transferred of 6,021. And then we go back to determine if that inner surface temperature of -5 is correct. This we can use as just a part of the thermal resistance network, so just T infinity 1 to T surface, and we find that we get -4.447 degrees Celsius, which is very close to what we assumed. My final problem, problem number 3, considers a company that's designing the handles for dumbbells. These are modeled as a short stainless steel cylinder, and we are to determine the temperature at the center of the top of the surface of the cylinder after 10 minutes. So this problem considers multi-dimensional and one-dimensional transient heat transfer, as well as cylindrical and Cartesian coordinates. I first began by drawing a picture seen here, where we have a side profile and front profile of this short cylinder. And for this analysis, we have to consider multi-dimensional transient heat transfer, which we can consider a short cylinder, a long plane wall crossed with the intersection of an infinite cylinder. And To begin this, we have to find the characteristic length for that plane wall, and then we're going to find the time dimensionless parameter and the BO number for the plane wall case. And then from here, we use those in interpolation on handout 8 to find A1 and lambda 1 for the plane wall, and we follow a similar approach now with the cylinder as well. And then we use the dimensionless temperature equation to solve for the dimensionless temperature of theta wall, as well as we use that yet again to solve for the dimensionless temperature of theta cylinder. One difference here that you'll see is that considering the center of the top of this cylinder, you have to include the length for theta wall, so you have this cosine term, and then for the cylinder, we're at R0, so you do not have the length here. And then since we're modeling this as a short cylinder, we simply can multiply theta wall by theta cylinder, as we each have one-dimensional transient heat transfer, and then by combining them, we have multi-dimensional spatial heat transfer. And we can relate this to the actual equation for this dimensionless temperature and solve for TS.